today, well, is Léonard Ferdinand, also from University Paris-Saclay, and he's going to speak about stochastic quantization for tensorial non-local field theory.
Well, so first of all, I also would like to warmly thank the organizers for this nice talk. So my talk is going to be about, I think, stochastic analysis meets QFT, and I'm also going to say a few words about critical theory, but okay, I'm not going to discuss the critical theory. So first of all, I'm going to introduce what are tensorial field theory. And fortunately, what Alexander Hook said this morning is a bit going to shed some light on what they are, but I'm going to anyways to explain and also to gather a few informations about, in general, non-local field theories. Then as a warm-up, and also since this conference is bringing together people from different communities, I'm going to recall some very basic facts about the stochastic quantization of local 543. And at last, I'm going to discuss how this, what the analogous techniques are going to take place for the case of this non-local T44 theory, which is analogous to 543 in terms of power counting. I'm going to discuss it. So, first of all, just to briefly recall the facts about the Euclidean quantum field theories. So, well, they are probability measures on some space of distributions, and we aim to construct them as some perturbations of the free field. Okay, it turns out that in one dimension, the free field is continuous and can be perturbed by, one Gaussian term, and well, in two dimensions, well, most of you must know that. It's logarithmic divergent, so it's supported in distributions, but that are almost like bounded functions, and one can still define some non-Gaussian perturbations, but what one has to perform one peculiar kind of normalization, which is called weak ordering, and the outcome are some non-Gaussian measures that are still absolutely continuous with respect to the free field. Okay, so later on, when increasing the parameter that governs the criticality of the theory, one encounters more renormalization, and the non-Gaussian measures stop being absolutely continuous with respect to the free field. But okay, let's say that in general, in the subcritical domain, one expects to be able to construct some non-Gaussian measures, and in the case of 5-4 models, the construction has been achieved, by various methods. Okay, maybe I will say a few words about it later. Okay, so in the critical dimension, the situation is different because there is an infinite number of counterterms, and because this implies that, the flow of the coupling is going to be fully taken into account, due to renormalization, and many things can happen. And okay, regarding 5-4 models, perturbatively, one can say that the coupling constant is going to blow up with scale. Not only is going to blow up, but also it's going to blow up in finite time, so to say. And this is a strong heuristic that points toward criticality. Okay, and this was made rigorous. So the 5-4 model is not a good example to investigate the critical dimension. Okay, in the supercritical regime, one can say that generally one does not expect non-Gaussian measures to exist. At least for 5-4 models, they do not exist. Okay, so the first conclusion on this previous slide is that actually we do not have so many good candidates to investigate the properties in the critical dimension. Okay, so of course there are non-abelian gauge theories, and it turns out that there is a theorem by Coleman that states that if you want to construct a local QFT, which is asymptotically free in the UV in critical dimension, it has to include non-abelian gauge theories. Okay, of course, like the standard model does, for instance. Okay, and it also turns out that, roughly speaking, non-abelian gauge theories are, let's say, difficult. Okay, there are many reasons why they're difficult. For instance, Martin Heyer was talking yesterday of the lack of coercivity of the Dirichlet action. Well, there are also issues with gauge fixing. So overall, they're complicated. And the theorem by Coleman, there are ways you can circumvent it, and you can say, okay, I'm going to look for some other critical theories, and maybe they're going to be okay, easier to deal with. Okay, and one hypothesis one can remove is actually the hypothesis of locality. Okay, so this. Okay, so now I'm just going to do a small disclaimer. As long as you, I mean, in general, locality is not a hypothesis you should remove. I mean, people familiar with algebraic QFT, for instance, know that many axiomatic approaches to QFT demand locality, and in particular, we are not going to today to deal with something that might verify axiomatic things, and in particular, they are not true QFT. They're more, okay, they are just a toy model to investigate behavioral criticality, okay? And also, I just wanted to point something. Coleman, in his theorem, is supposing that the coupling are positive, and maybe it's possible to construct some actions that are going to be critical, but with complex couplings. Okay, and actually this was done recently by Razvan and also other collaborators. So he created a local field theory, but with complex couplings, and it looks like perturbatively it is asymptotically free in the UV. Okay, so now I'm just going to say more in detail what tensorial field theories are, and just a small disclaimer: they are not like local theory with indices. Okay, so they are not what we could call linear sigma models or tensor models or ONT models. Okay, sorry, maybe this could be confusing, but they are a field theory in which the power counting is also going to involve a quantity that has to do with the Lagrange expansion for tensors. Okay, and in practice, it's made in the following way. So since the things are non-local anyways, it's better to work on the torus. And on the torus, one can identify phi with its Fourier components, and the Fourier components are a tensor. And the interaction is going to be precisely given by tensor invariant for this tensor. Okay, so well, this expression is can be pictured in this way. So any node of the graph is just going to be one copy of the Fourier components of the field, and the edges just represent the identifications of the indices in some direction. So overall, this interaction, it's really, one has to think of it really as not a local product, but as many pairings. So actually, well, 4 pairings. It's okay, so it's like the interaction was L2 to some power, but actually it's L2 in some directions, and you do something that is cyclic. Okay, I hope this heuristic is convincing. And of course, the kinetic term is going to be what corresponds to the free field. So for instance, in Fourier, it is like this. These models were introduced by Joseph and Vincent 13 years ago. And okay, so also since I'm going to deal with stochastic quantization, I've forgotten to say, but I think it's good to see how the interaction reads in direct space. And in direct space, since the interaction is made with pairing, it's somehow the same one in direct space. Okay, contrary to local product that becomes convolution and vice versa. So once again, one has to choose 2 points, and the 2 other points are given by the structure of the vertex, and the interaction is simply the integration of the 4 fields, 4 copies of the field at the 4 different points. Okay, and one is interested that the TFTs that are going to be constructed as some regularized and renormalized weak limits of the free field times this interaction. And of course, well, as in the local case, one should take some varying parameters that depend on the cutoff that I call rho t. It's just, okay, so modified free field. Okay. So at the perturbative level, the power counting is given by that of the local theory in d-1 dimensions minus the degree. And the degree of the graph is a quantity that roughly counts you the number of faces. I'm just going to show in one slide what it's about. And just for the record, because the power counting of the local graph just tells you that the more external edges and the more vertices, the more convergent the graph. And actually, the more vertices it holds in the subcritical case. In the critical case, you have no gain with the number of vertices. Actually, at fixed number of external edges, all the graphs share one same power counting. Okay, so this means, and this d-1 here just means that T for D is going to be analogous to T to 5 for d-1, and this minus D here is going to mean that there are going to be less primary divergences, and the primary divergences are just going to be the melonic graphs. Okay, and just, okay, so to explain what a melonic graph is. So this is a graph. I mean, it's a graph of the local theory. It's a two-vertex graph. Okay, it turns out that it has two tadpoles. This is not so, okay. This is just an example. And once one plugs the non-local vertex inside the graph, turns out that there are many ways to plug it inside. So you can put it this way, and this holds for both vertices. So overall, you are going to create many different graphs, and these different graphs, they are going to have different numbers of faces. Okay, so by faces, I mean Fourier component, which is summed when computed the amplitude of the graph. So this is one face, and actually there are d-1 faces here. This one here is also one face. So this graph has many faces, and this graph has less faces. In particular, this one is the melonic version of this local graph, and this one is one of the many, actually here, maybe 3 non-melonic versions of this graph. Okay, so if this graph is going to be divergent in the local theory, actually it is going to be divergent because it has tadpoles. This graph is going to be divergent, but this one is not going to be divergent. Okay, so second fact about the TFTs, tensor field theories. The theory is critical in five dimensions, sorry, and turns out that it is critical. So this is one of the reasons why we are interested in these theories. And okay, I'm not going to explain today why it is asymptotically free, but turns out that, okay, maybe it's going to be too fast, but in the local case, wave function renormalization begins at order G cube because the tadpole is local, and so it's after mass renormalization, there is nothing left. But in this case, this is not the case, and so wave function renormalization contributes to the coupling constant renormalization, and actually it dominates and changes the sign of the beta function, which explains why one expects asymptotic freedom in the UV. Okay, so now I'm just also going to discuss some other non-local field theories, and well, okay, because TFTs are included in a more general framework. So the equivalent to tensorial field theories for the vector is just putting the L2 norm as an interaction. Okay, this is something which is a nice playground because it's very easy, because in the full subcritical regime, you only have to consider the tadpole renormalization, and the renormalized action is still positive, okay, due to this observation. So there is a simple construction. Actually, since the Hamiltonian is positive, it's even bounded by 1, but this is also trivial in critical dimensions, so it's not so interesting. Okay, and then there are matricial field theories, and in particular, Alexander explained that the Moyal product can be rewritten a bit in the same way that we did, but instead of the tensorial interaction, you just have the trace of the fourth power of the matrix, and also the kinetic term is not going to be Laplacian, but square root of Laplacian. But okay, this is, of course, the most interesting example of non-local QFT. It's asymptotically safe in the UV, and it was constructed. So, okay, so I've already discussed TFTs. I just wanted to say that there are already some constructions of the analogous to 542 and 543, and that they have Borel summable log partition function in the coupling constant. So this is, okay, this is one information about the distance of the measure. This is a bit different from what we're going to discuss today. And also, I just wanted to say that there also exists a non-local field theory, which is the Hartree nonlinearity, and which was already studied in the context of Langevin dynamics, also wave equation, by Brinkman and Okamoto and Tolomeo, but it's different from what I'm going to discuss today, because the Hartree nonlinearity is based upon the local product or convolution in Fourier. So somehow you can use the same tools that you use for local 5-4, and it's just a smoothened version of the local product. So yeah, actually these authors study it with the tools of power control calculus. Okay, and to conclude about the TFTs, I'm just going to present briefly what are the differences in terms of power counting in the subcritical regime. So for the record, this has been discussed extensively during these days. In 3 dimensions, there are 2 divergences, primary divergences one has to deal with for 5-4, the tadpole and the sunshine, sunrise, sunset. So today it's going to be sunset graph. And for people coming from the stochastic community, I also draw some expectations that have to do with these graphs in the, when regarding the divergences of the amplitude, perturbative amplitudes for the measure. Okay, but there is something which, the tadpole, once the amplitude of the renormalized, of the tadpole is renormalized, its amplitude is 0. In particular, for 543, this graph is going to be 0 already since the tadpole inside is renormalized. Okay, so for 5,4, things are different. The tadpole has a renormalized amplitude, and in particular, even if it's nested inside this graph, and even if the tadpole here is renormalized, this graph can still be divergent. So it's one of the primary divergence one has to take into account. And regarding the sunset, however, there is no way plugging here the non-local vertex, you can build a melonic graph with the solve set, which means that the solve set is always going to be convergent, or well, say it's not primary divergent of the non-local theory. So I'm going to discuss later on the consequences of this difference, but in general, to conclude about the renormalization in the subcritical domain, so roughly speaking, the divergences of T44 are always going to look like some snowballs, which means they are always going to have this tree-like structure, which is also the tree-like structure of the melonic graphs. So there are not so many, and in particular, there is a in the critical dimension, you can it's the number of divergent graph is exponentially bounded, so you can also expect to resum all the counterterms one has to add to the measure in order to define the critical to define it in the critical dimension. So now I'm going to discuss a bit slowly than Viet did how the stochastic quantization, and in particular the Landron dynamic approach, works in the local case. And this is going to serve us then to draw a comparison with what's going on in the local case. But right now, the take-home message is going to be that things are easier, in many regards in the non-local case, which is great and which we're going to be able to discuss. So the idea of Landron dynamics, but Viet has been explaining very well why this is one candidate equation, is that if the measure exists, it is invariant under a certain PDE, stochastic PDE, and so means that solving this PDE can also help us to construct the measure. Well, but there is an issue with this PDE. It is that in the dimension in which one is interested in it, it is singular, due to the rough character of the noise, which in 3 dimensions is going to be of regularity minus pi/2, actually minus, whatever that means. And since this operator here is, it's the hit operator, and it behaves like a 2 regularizing operator, one does not expect the field to be better behaved than -1/2, which does not allow us to give meaning to the nonlinearity, by the Young product estimate. So the starting point is always going to be regularized and renormalized equation. So there are many ways in which you can regularize here. I'm just cutting the frequencies in the noise and in the interaction, but this is a bit arbitrary. But the important thing is you can inherit what you know from the way in which you set all the perturbative amplitudes to a finite value. You can make some guesses on what you will have also to add to the equation, the divergent quantities you are going to have to add to the equation in order to then to obtain a solution theory. So this is the first step, and the second step is to say that, well, this equation is a nonlinear PDE, and you might say naively, I'm going to solve it by a Picard iteration. So this you can do, but you can refine the argument and say, maybe I can hope that my solution is going to look like the Picard iterates of the noise. So the Picard iterates are, well, they are what you obtain when you need, say, I'm going to solve the equation by first linearizing it and then reinjecting the solution to the linear problem. Okay, but it turns out that, I mean, you cannot do this because you cannot construct some nonlinearities even for the free field from the noise. So sorry, this is, I'm going to call the solution to the linear equation the lollipop, and it turns out that the way we do it, it's equal in law to the free field. So sometimes I'm going to say the free field, even if it's not super rigorous. Okay, but okay, so in order to construct all the Picard iterates, one has to renormalize different products of entering the composition of the Picard iterates, and this is done by using the counterterms that we put inside the equation. Okay, so now that we have this idea, we're going to say, okay, I'm going to, and maybe my solution looks like the first Picard iterates, so I'm going to use it as an ansatz, and I'm going to say that I'm now going to look at the equation for the remainder. So now here is the equation for the remainder written, and okay, it turns out that this equation still exhibits two difficulties. Okay, the first one is that now the purely stochastic term is no longer the noise, and it's something which is, okay, constructed by renormalizing the third power of the free field, and it's a well-defined object, and it turns out that in the subcritical regime, it's better behaved than the noise, so sorry, no, not, yeah, sorry, better behaved than the noise, which is nice, but it's still so rough. Okay, so it's of regularity -3/2. So adding the +2 coming from the operator L-1, we would have V, the solution, which would be a regularity 1/2. But one, on the other hand, aims to multiply V with this object, which is a regularity -1-. So this term is still a problem, which means that one should push further the argument, which is called Dapatot-Bush argument, or Bourgain argument, by the way. The fact to say, okay, maybe my solution is going to look like the Picard iterates and to use them as an ansatz. Okay, so this is the first thing. Okay, but there is a more worrying problem, which is the fact that actually this product of the second weak powers time V is never going to be well defined. Okay, because this product is like this object going to be of regularity -1-, which entails that V cannot be better behaved than 1-. And okay, so Young estimate in this case does not hold because the two regularities do not sum to 0+. Okay, and this second regularity is more critical, and for a long time it required new ideas, and eventually people said, okay, so maybe one should know this term better. Okay, and split it in two parts. Okay, the aim is to say, okay, this product, it has two difficulties. It's not well defined because the regularities do not sum to 0, and it's too rough. So it forces V to be too rough too. And one can separate, and the idea is one can separate the part which is singular, which doesn't exist, from the part which is responsible for the regularity of the object. Okay, so one would like to separate as something which is a regularity -1- and something which is more regular, but in general does not exist. Okay, and then once this is done, the strategy is to say, in the same way that we removed some stochastic object by the Dapatot-Bush argument, we could also remove this thing and actually add it to the ansatz and see if the remainder obeys okay, better behaved equation, an equation that can be solved by a fixed point argument. And okay, the outcome is that the expansion is now going to not only depend on some purely stochastic things, but also going to depend on the solution itself. Okay, and in practice, there are mostly two ways to realize it. So one in direct space, in which you say, okay, so f of y, g of y is going to be f of y, g of x, okay, where f is a rough thing. So now v here is a constant, so this looks like this, and in particular, it's still rough, but it exists. I mean, just because v is not taken at the same point, so it's like an exterior product of two distributions. And to recenter v, and you know that if v is a positive regularity of function, so say a Hölder function, of course, a Hölder function, which is alpha Hölder, does not behave like x -1 alpha, but once recentered, it does. And this also, so it's suggesting an ansatz which is, okay, I'm going to add it to my ansatz, and actually it's even better. I'm going to also recenter the subject to always have terms which behave well. And okay, this is the idea behind a very large framework, which is regularity structures. Okay, and to which contributed many people. I'm just giving the names of many people we were here during this conf. And also one has a different idea, which is in Fourier space. So the local product in Fourier is given by convolution, and convolution distinguishes the sector in which one of the modes of the rough distribution of the Böder-Behave function can be high and low, and in particular the regularity of the object is going to be dominated by the sector in which only the rough distribution has high modes, so larger than the modes of the function. And it turns out that the remainder is more regular. But the good news is that this part, even if it's rough, is always going to exist. Okay, these are the para product Viet was talking about. And once again, this suggests an ansatz, and also there is a wider framework which is called para-control calculus, okay, and which was introduced by Kubinelli, Imkeller, and Perkowski. Okay, so now I'm going to be able to discuss the renormalization and the ansatz for the Langevin dynamics for the T44 equation. So T44 is a model which is analogous to T43, and I'm going to be able also to discuss the differences and the common points with the picture in the local case. So the regularity, the nonlinearity, sorry, that comes with the quartic-melonic interaction, so the interaction I presented during the introduction, is given by this expression. And since the interaction was bilocal, so there were two integrations, there is still an integration inside the nonlinearity. Okay, and the way you can see it is you have this quartic interaction, and you take three functions, and you put them at three of the nodes of the quartic interaction, and this is the nonlinearity. Okay. Once again, one has, as a starting point to study the Langevin dynamic, one has to consider a regularized and renormalized equation. And now I'm also going to add two counter terms. The first one will still have to do with tadpole renormalization, I would say, rather than weak renormalization. And now the second one is not going to be here to take it in charge sunshine divergences, but rather snowball divergences, you know, the graph with a nested tadpole inside. Okay, so once again, one says, maybe the solution is going to like the free field or the lollipop, so we're going to be able to do one step of Dapper-Bush expansion, and one obtains this equation, which is the same than in the local case, but now the project is non-commutative, so we have more terms, but it's not so important. And I'm going to focus on two terms. But there's something I have not been discussing too much in the local case, which is the fact that after one step of Dapper-Bush trick, the first renormalization is absorbed in order to construct the stochastic objects, for example, this one here and this one here. So this also holds in this case, in which, okay, we are now left with explicitly the second renormalization. So now the first question is, what is going to be the meaning of the purely stochastic objects? So for instance, this term, and also from part of this part of this big term, for instance. And okay, so it turns out that the question is twofold. It is, what are going to be the regularities of the terms? And if they have some divergences, how are we going to cure them? Okay, and so the thing is, when one takes the expectation of what corresponds to the third power of the free field in the non-local case, so now there is not going to be only one term with a combinatorial factor 3, but there are going to be several different terms. And according to the choices of free fields that are contracted, one obtains different expressions. And as I anticipated, the non-melonic one, so the one that corresponds to non-melonic graphs, are not going to be divergent. So renormalization is not going to be given by weak renormalization or projection onto another Gaussian chaos. Okay, one is just going to remove part of the projection onto the first Gaussian chaos. And actually, not only is not given by weak ordering, but also the amplitude one obtains when, okay, considering the projection into the first Gaussian chaos, is going to be a sum, and this sum, okay, so as expected, it's diverging like a d minus swift. In field dimensions, it's logarithmically diverging, and then in the critical dimension, it's quadratically diverging. But this sum is not a constant, okay? Like the amplitude of the tadpole in the local theory, and in particular, one does not remove this constant, but only its local value, or its value at zero external momentum. Okay, so this is what is explained here. And here I just explain it in direct space. So in direct space, zero external momentum is now, it's one, you know, the Fourier transform of one is delta 0 n. So one does not remove the expectation, but the expectation with the local part of the expectation, and one does not remove the whole expectation. There is no factor 3, but only the part of the expectation in which the lollipop 3 is contracted with the lollipop 2. Okay, so this is 1/3 of the total expectation. Okay, so this is, to summarize, renormalization is not given by weak ordering, and it's not local. Okay, so it's a bit different. Okay, so now there is the second question, which is, once this object exists, what is regularity? And a bit surprisingly, its regularity is not given by the sum of the bad regularities of the distribution of the free fields, like you would expect. For instance, in the local case, so sorry, for the record, we are in 4 dimensions. So the lollipop, it's -1. It's not -1/2 like in Viet's talk. But there is this +1, okay? And it's going to be a very general fact, okay? It turns out that this quartic melonic tensorial nonlinearity has something which, okay, I would call the regularizing effect, but it's something which is purely stochastic, okay? Of course, it's not related with anything deterministic. And just to show how things are going on and where this +1 comes from. So these things, they belong to some Gaussian chaos, so there are hypercontractivities. So one is only interested in second moment computations, and one considers Sobolev norms. So I take 2 copies of the object and I compute its Sobolev norms. So the m to the 2 beta means, I'm computing the Sobolev norm. And okay, I'm going to take the expectation. And when taking the expectation, now there can be many contractions. So actually, okay, 5 times 3, so 15 contractions. And only one of these 15 contractions is going to be melonic. So it's going to be the melonic one, so the one with more faces. So it's going to be the one which is going to give the worst upper bound on beta. Okay, and it turns out that when one counts the number of faces, okay, then the number of propagators, that gives some factor -2, etc. We arrive with this +1. Okay, so this is like in the local case, but the difference is that there are many contributions, and we also have to control that the other contributions are better behaved. Okay. So I'm going to come back to the importance of this +1 later on. Now, there are all the other terms, which are the mixed terms, which one has to interpret. Naively, so for instance, this one, first of all, it can be defined without renormalization, because actually this lollipop and this lollipop don't see each other. They really are like an they really are an external product of 2 functions. So there is no issue with existence or renormalization, but yet these terms is a priori ill-defined, because you say, okay, so this term exists, it's a well-constructed distribution, but since the free field is of regularity -1, its tensor product with itself is going to be of regularity -2, a bit like, you know, delta in dimension 2 is -2 because delta in dimension 1 is -1. Okay, and so this would require to be able to plug V inside V to be of regularity +2, but of course -2 you don't expect better than 0 and in particular you don't expect 2 So we have to do something for this kind of terms, and we see them as some random operators acting on the solution. Okay, and it turns out that, okay, we are going to be able to compute the regularity of this random operator here, and so now we say that this is here evaluated at V, and it turns out that if you take V to be of regularity alpha, then the output is going to be of regularity alpha -2. Okay, once again, well, the computation is similar, but now, okay, so now we are going to put some v's when drawing the two copies of the object. And okay, we say that v at some Fourier mode is going to be controlled by the subleft norm of v. And okay, so it's going to add a new edge to the graph probing the regularity of v. And once again, one has to take all the possible contractions. Once again, there is going to be a contraction that has the smallest degree. Turns out that here it's not melonic, but okay, it's the one that has the smallest degree. And okay, we are going to obtain a condition on beta. And now this condition on beta is going to depend on alpha. So we are going to have a relationship between alpha and beta. So actually, to be precise, one also has to check that all the subgraphs of these graphs also are convergent, and this gives more conditions. So for instance, when I say that beta has to be smaller than alpha minus 2, this holds for small alpha. But if you put alpha is equal to 100, you cannot go to 98, of course. You're always going to be at something like -1/2. Okay. And this also has to do with, for instance, positive renormalization, meaning if you multiply a rough distribution with something very regular, you're not going to see the regularity of the regular something you're multiplying with. Okay, and we are in the same way, so we are defining in this way all the mixed terms. Sorry, all the mixed terms. So we're also going to define some random operators for the other mixed term. So for instance, we are defining a random operator which corresponds to the free field, but now contracted in some direction with some deterministic function. Okay, and it's better behaved than this one. So this one is going to be the problematic guy. So you see here there is alpha minus 2. This one is better, alpha minus 1. So I'm mostly going to discuss this one. Okay, so now after everything I said, the equation looks like this. So many terms we have defined. There is still this stochastic object, which is a regularity minus 2 minus, and this random operator that maps C alpha to C alpha minus 2. Okay, and we still, like in the local case, have two issues. The first issue is the regularity minus 2 of the purely stochastic objects prevents this operator from being well defined. And the answer is we're going to push forward the Daplateau-Debush expansion. And when pushing forward this Daplateau-Debush expansion, we are going to define new stochastic objects, and we are going to use the remaining renormalization. And here something very nice is going to happen, which is the fact that contrary to the local case, defining these objects is going to use the remaining renormalization constants. So after enough Daplateau-Debush steps, the equation is fully renormalized, meaning that there are no explicit contour terms left. And this is happening also in general in the full critical regime. And there is a reason, and I mean, heuristic reason for this, which is the fact that in the local case, the divergences, the missing branch inside the graph, which is responsible for the divergence, is in the past. I don't know. So this is a Picard iterate, so this is a present t, and this would be a S which is integrated from -infinity to t. So the renormalization involves also looking into the past of the remainder. Whereas in our case, renormalization, as I was saying, is easier. And in particular, if the missing branch is always going to be in the present. Okay, so simply further in the subcritical regime, these two trees are going to be bigger, of course, but yet they are just going to be here and here. So phi is not going to move inside these two trees. So this is one nice feature. Okay, also, no, okay, but okay, this is nice. There's something which is less nice, which is the fact that after many Daplateau-Debush tricks, one is going to be considering, okay, say cherry times the big tree, and it turns out that now the big tree is very regular. So one needs this object to be more regular than the object one has with the smaller tree here. But since these trees have positive regularity, this does not happen in the same way that, okay, you cannot expect to regularize the distribution by multiplying it by the very smooth, very regular function. And okay, so but we can circumvent this difficulty by rather saying this, okay, we do not evaluate it by stochastic means, but deterministically, we just view it as this random operator acting on this object. Okay. Okay, so now we have been further in the Daplateau-Debush expansion, so we have no renormalization, we have no, and all the terms are well defined. But this term, I'm coming back to what I said before, which is that this operator, it maps C alpha to C alpha minus 2 minus epsilon. Okay, and this is, okay, it's a very big problem because, you know, L is too regularizing, which means that for this term composed with N is going to map C alpha to C alpha minus epsilon. So it goes to a bigger space, okay? It's not a contraction, and in particular, the fixed point map doesn't close, okay? But here one can remember that the purely stochastic vertex was +1 regularizing, but for it to be +1 regularizing, one has to put inside some purely stochastic expressions, which is not the case here, since here the argument of the random operator is deterministic. So it turns out that if one composes the random operator with itself, which defines, okay, a new random operator. So if when we insert the random operator into itself, so now there are two vertices. So yeah, there are two vertices, and of course this one is still going to be not purely stochastic because there is still V inside, but the one below is going to be purely stochastic, and there is going to be here this +1 effect. And this new random operator, instead of being, say, of regularity alpha -2, it's going to be of regularity alpha -1. Okay, so this, for the moment, this is nothing. I'm just creating a new random operator, but this is suggesting to us an ansatz in which, well, we get rid of this random operator, but by trading it for the new random operator, and now the equation is, I mean, the fixed point map closes, so we have local existence of the solution. Okay, and just a small remark, of course, what we are doing, it's because we are lucky. I mean, these are not new ideas. They simply are stupid in the local case. You cannot plug the cherry times V inside L-1 of cherry times V. You are not doing anything better. Okay, it simply does not work. It does not improve, and actually it's not well defined. Okay, so now just a last thing in which tensorial field theories are easier than the local case. So now I've been discussing with normalization and the ansatz for the Langevin dynamics. There's also a nice feature which has to do with the construction of the objects. And I wanted to discuss it also because in this seminar, we've been discussing many Feynman graphs in the stochastic analysis context. And I wanted a bit to fill the gap between usual Feynman graphs and these Feynman graphs. Okay, and it turns out that in this context, there is an equation for which there is a Duhamel operator, and this Duhamel operator is just, okay, it's the heat operator, and it's going to be one possible propagator, okay? But there is a second propagator that arises when one computes some expectation, and which is the covariance of the free field, but with a sort of mollifying. I mean, it's computed between two different times, and so it's a smooth version of the covariance of the free field. Okay, and the result is that you can look at the graph from the theory, from the measure, and from the perturbative expansion for the measure, and this graph is going to correspond to some different amplitudes in the stochastic analysis context. So for instance, the sunset, you can draw it by putting 3 parallel covariances of the free field, but smoothened covariances of the free field, or you can draw it with one of the edges, which is a Duhamel operator. Okay, and it turns out that these two expressions are very different. Not only they are different, but also one of them is divergent and the other is not divergent. So this is a huge difference. And this one is not divergent because of this smoothing here. Okay, here there is one time, here there is another time, so you have room to absorb the logarithmic divergence of the sunshine. While here you really see the divergence. In particular, this one is going to come with the renormalization, and this one not. Okay, and this also implies that one cannot naively use the knowledge from the perturbative expansion to bound the stochastic amplitude. Okay, because you could say I would like to bound, for instance, the left amplitude by the sunshine, but you are going to bound something that does not have a contortum. Of course, it's finite, but it does not have a contortum, but by something which would require a contortum. So this is true. Of course, this is a good bound, but you are bounded, for instance, something finite by plus infinity. So that's not efficient. Okay. So ultimately, you can't do this. While in our case, well, a moment of reflection shows that there is only one way in which you can draw the tadpole or the snowball. I mean, and the only snowball that exists is the one with here one Duhamel operator and here one covariance of the free field. So this one also comes with a quantum, but there is a one-to-one correspondence between our graphs and the perturbation theory graphs. So we can, okay, roughly bound our amplitudes by the perturbative one. And it turns out that, okay, then we can use what we know about the perturbative amplitudes to construct our stochastic objects. Okay, so this is also a nice feature that simplifies the construction because, yeah, we go back to some theorems, yes, for perturbative amplitudes like multiscale analysis. Okay, so to conclude, I would just like to conclude by a conjecture, which is the fact that the ansatz I've presented, but okay, generalized, of course, and pushed further, should cover the full subcritical regime for, yes, for the Langevin dynamics. Also, as I said, the interaction is a norm. So we can use the coercive character of this norm to show tightness of the law of the invariant measures. Well, it's less coercive than the local norm, than the L4 norm. So what we find is, I mean, tightness in a worse space, but nevertheless, we show the existence of the invariant measure. And also we have used the ansatz to plug inside the variational approach introduced by Barashkov and Gubinelli, okay, which is another way to construct the measure. Okay. Thank you.